This is the fourth video on Chapter 33, Derivatives and Graphs. What we're going to do different in this video and the next is we're going to look at intervals of concavity and inflection points. So we're going to start with the third degree polynomial. Because it's a polynomial, it has no asymptotes. So the fact that it's a polynomial implies there are no asymptotes. We're going to look for the intervals of increase and decrease the way we always have. We're going to calculate the derivative of f, factor the derivative, make a sign chart. The roots of this polynomial are 0 and 2. We put those on the sign chart. When x is very, very small, well, this is a negative times a negative, which is positive. This is a second degree polynomial that opens upward. So it opens upward, it has two roots. So we know that it's going to go positive, negative, positive. But when x is between 0 and 2, this is positive, this is negative. A positive times a negative is negative. When x is large, we have a positive times a positive, which is positive. Our function's decreasing on the interval 0, 2. It's increasing on the intervals negative infinity to 0 and 2 to infinity. When your function goes from increasing to decreasing, that makes a local max. So we have a local max of 1 at 0. When your function goes from decreasing to increasing, that makes a local minimum. So we have a local minimum at 2. So we have a local minimum of negative 3 at 2. And now we're going to look for the intervals of concavity and inflection points. For that, we use a test for concavity, so we'll take the second derivative of f. The second derivative is 6x minus 6. Factor out the 6. We have one root, which is 1. Our second derivative is negative when x is small, positive when x is large. So our intervals of concavity, we have negative infinity to 1. That's where our function is concave downward, concave upward, 1 to infinity. That's where the second derivative is positive. So when the second derivative is negative, your function is concave downward. When the second derivative is positive, it's concave upward. Another difference, you'll notice I did not include the 1s in the intervals. These are parentheses, these are not square brackets. That's because concavity is a property that a function has on an open interval. When you look at the definition of what it means for a function to be concave upward and concave downward, those are defined in terms of open intervals. So your intervals of concavity will always be open intervals. Your function changes concavity at 1. Goes from concave downward to concave upward. That means there's an inflection point at 1. F of 1 is negative 1. Here's the thing to keep in mind about an inflection point. An inflection point is a point on the graph of the function. So an inflection point, 1, negative 1, that is the place on the graph where your function changes concavity. But an inflection point is a point on the graph. Okay? I'm making that point. So if we look at part B, I'm not going to do a video of part B, the whole thing. But I'm showing you the graph right here because you might have a question on the inflection points. When you look at the notes, you'll see that it says inflection points none. There are no inflection points of that graph. Why? Your function does change concavity. It's concave upward here, concave downward here, concave upward here. So your function does change concavity. It goes from being concave upward, concave downward, concave upward. But these are vertical asymptotes. The function in part B is not defined at negative 1 and it's not defined at 1. There are no points on the graph at negative 1 and at 1. That's why there are no inflection points. An inflection point is a point where the function changes concavity. This function changes concavity, but it does it at the vertical asymptotes. It doesn't do it at any particular point. That's why part B has no inflection points.